guys, welcome to another video. This is Massey. This video I want to talk about law of electromagnetic induction. As you know, an electric current is induced in a conductor whenever the magnetic field in the region of the conductor changes. So in this example, it says each circle in figure below, like this, represents a conductor which is part of the loop of wire not shown. In each case, state two ways of inducing a current in the conductor. So, inducing the current in the conductor, it means that we need to somehow change the magnetic field in order to have induced current in the conductor. So, it means that we need to move the conductor in somehow that it experiences change in magnetic field. How that happens? If I show you the magnetic field lines, from N to S, it means that if we move this conductor up and down, or if we move it in direction of perpendicular to the page, it means that going in and out, nothing will happen to the conductor. So there will be no change in magnetic fields, and then there is no induced current. But if we change the conductor in this way or this way, it means that we're gonna cross the magnetic field line. In that case, the conductor experiences different magnetic strength. So that's why we will have induced electric current in the conductor. So when it moves this way or this way, we will have induced current. Same thing here. If we go this way or this way, we're gonna have induced current, and also this way, it's gonna cross the magnetic field line, and then it results in induced current. Next example, it says a bar magnet is used to induce a current in a coiled conductor. State the effect of the current in each of the following circumstances. Part A, it says when the number of coil windings is increased. So it means that when we increase the coil winding, we're gonna have more induced current. Based on law of electromagnetic induction, so when we increase the number of turns in a coil, we're gonna have more induced current. Part B. The speed of magnets relative to the coil is increased. That's related to the rate of change of inducing magnetic field. And we know, based on law of electromagnetic induction, the rate of change of the inducing magnetic field is going to be proportional to the induced current. So, as you increase the speed, we're going to have more induced current. So that increases. Part C. The strength of the magnetic is increased. Yes, that's due to law of electromagnetic induction. When we increase the strength of the inducing magnetic field, we're going to have more induced current. So we can say induced current increases. And part D, the magnet and coil move at the same speed in the same direction. Same speed in the same direction. Since both of them are going in the same direction, it means that theta is going to be 0. So we will have no induced current. because inducing magnetic field doesn't change. It doesn't change in direction, it doesn't change in area, it doesn't change in terms of strength. Now, figure below shows a loop of wire inside a uniform magnetic field. Which of the following will produce an induced current in the loop? Part A, the wire is moving up or down. So, when the wire is going up and down, there is no change in magnetic field. There is no change in surface area. And there is no change in the angle between the wire and magnetic field. So, part A is going to be no induced current. In part B, it says it moves horizontally out of the magnetic field. So, when it is going outside the magnetic field, it drops. So it's going to induce current. Part C, it says the loop is rotated. So since loop is rotated, the theta is changing. So that's going to induce current. And part D, loop is compressed, decreasing its area. So A is reducing. So that's going to induce current as well. Next example is saying a closed circuit is placed near a non-uniform magnetic field of a bar magnet. Why would it be difficult to move a circuit without producing an induced current? So it is difficult because changing the location of the circuit is gonna make it exposed to different magnetic field strength. So since it's gonna experience different B values, so it is gonna induce current because of changing magnetic field strength. Next example, it says determine the direction of the electric current for the case in figure B. This figure is related to Lenz law. Lenz law is saying that for a current induced in a coil by a changing magnetic field, the electric current is in such a direction that its own magnetic field opposes the change that produced it. For example, in this case, this magnet is going down. In this side we have south pole or S pole. This side we have N pole. Since we have removal of magnets, we need to have N pole in this side of the coil in order to oppose the removal of the S pole of the inducing magnetic field. So it's going to be N pole here and it's going to be S pole in here. Then we need to use the right hand rule. Thumb is going toward N pole, and when you rotate your four fingers, it's going to show the direction of these wires. It's going to go like that. So that's how we have this induced magnetic field. Now in next example, it says determine the pole of the bar magnet that is being inserted into the induction coil in figure below. So the first thing I need to do, I need to apply the right hand rule to find out N pole and S pole on the coil. If I use my right hand and rotate it, it means that this side is going to be N pole. This side is going to be S pole. So now, based on what I have, I need to figure out what pole I have in this side. According to Lenz's law, the pole of the bar magnet that would be opposed by this N pole as it enters the coil, so that's going to be N pole as well, because it's going toward the coil, and we need to have inducing magnetic field in order to oppose to this N pole in here, because it is inserting into the coil. If it was removing, then in that case it would be S pole in here, not N pole in here, or N pole in here and S pole in here. It's going to be opposite when we are dealing with removal of bar magnets. Now in this example, we need to find out the polarity of the induced magnetic field in figure below and the direction of the induced electric current. So we need to use both Lenz's law and also law of electromagnetic induction. So let's start from part A. Part A, as you see here, we are inserting this magnet. So since it's going inside, we need to have a N pole in here to oppose to that insertion, and this side is going to be S pole. Then I need to use the right hand rule. Thumb is going toward N pole, and the rotation of the four fingers is going to be toward this side. Like that. Like that. Now part B. Part B, S is going inside this coil. So again, from Lenz's law, we need to have S pole in here in order to oppose to this changing magnetic field. So N pole in here, S pole in here. So again, I need to use the right hand rule. Thumb is going toward North Pole, up. So location of this is going to be here. Next one. Here we have removal of S pole. So in order to oppose this action, we need to have N pole in here to attract it. N pole to attract this S side. So here we have N pole, here we're going to have S pole. Then I use the right hand rule. Thumb is going toward right, and the rotation of four fingers is going to be this way. In order to oppose this change. Next one, we have removal of N pole. Again, in order to oppose that, we need to have S pole in here and N pole in here. In order to oppose that, then I use the right hand rule. Thumb is going toward left, and the rotation of four fingers of the right hand side is going to be that. Is that going to be the direction of the induced electric current.